In the following example, we're going to try and construct the following redox equation using standard electrode potentials. And the equation we are supposed to construct is vanadium V solid reacting with excess Fe3 plus aqueous. Remember, Fe3 plus is in excess, so even at the end of the reaction, it would be still remaining in the solution. This is going to be a type of chain reaction in which one after the other, the reaction keeps on going, and the excess Fe3 plus keeps on reacting because you have a lot of Fe3 plus. So any products formed in the first step are going to again react with the excess or remaining Fe3 plus aqueous. Step 1 now is that we need to identify our reactants, and since the ions are already given, so we don't need to actually identify them. They're already there. There's vanadium, and it's a neutral metal. So remember, we're dealing with vanadium neutral, not vanadium ions. Similarly, Fe has a charge of 3 plus. So remember, we're not dealing with Fe2 plus or iron neutral. It's Fe3 plus aqueous ions. So identifying our reactants, we've already done that. Moving to step 2. Step 2 is that we now need to find all electrode reactions, or we need to identify all electrodes that involve vanadium, neutral vanadium, or Fe3+. Now for this, I would have to refer to the data booklet, and I'm going to try and find the reactions of vanadium first, electrodes that involve vanadium. So here's my data booklet that has all the electrode reactions, and we are searching for vanadium and neutral vanadium. So the electrodes involving vanadium are given over here, but there's only one electrode that has vanadium. For example, this electrode over here has vanadium 2 plus ions, and it's in equilibrium with vanadium 3 plus ions. I'm looking for only vanadium. So none of these electrodes, they contain vanadium neutral atoms, only this electrode over here. So I'm going to mark this electrode. This is the electrode that I'm going to use, and it has an electrode potential of minus 1.20 volts. The other electrode that I'm looking for involves Fe3 plus ions. So I'm going to search for all those electrodes that have Fe3 plus in them. Fe3 plus gaining electrons or losing electrons. We're not sure yet. We're not concerned with that. We're only going to take those electrodes that contain Fe3 plus. So if you look carefully, there's one electrode over here that contains Fe3 plus ions. Then there's another electrode over here that contains Fe3 plus ions. And the electrode potentials are given as one has minus 0.04 volts, where Fe3 plus is gaining electrons and forming Fe, and it's in equilibrium. In the other electrode, Fe3 plus is gaining only one electron to form Fe2 plus, and they are in equilibrium. And that has an electrode potential of 0.77 volts. There are no other equations where Fe3 plus ions, only Fe3 plus ions are involved. For example, over here iron 3 hydroxide is present, but we don't have iron 3 hydroxide. We only have iron 3 ions. So I'm going to only search for iron 3 plus ions, and these are the only two electrodes I could come up with. So I've copied all the electrodes that had Fe3 plus in them. There's Fe3 plus gaining 3 electrons, forming Fe3 plus gaining an electron, forming Fe plus 2, and I also copied the electrode that had vanadium in it, vanadium in equilibrium with V2 plus. So I've copied all the 3 electrodes. These are the electrode potentials. Now the rule is that higher potential is the one that's going to gain electron, and lower potential is the one that's going to lose electrons. So I have 3 electrodes. The highest potential is shown by this electrode over here, 0.77 volts. So this is the one that's going to gain electrons, and it's going to go in the forward direction. And since this is the one that's getting reduced or gaining electrons, it's Fe3 plus that's gaining electrons. So I have to ensure that the reactant in this electrode over here, since it's gaining electrons, Fe3 plus is the one that's gaining electron, and we do have Fe3 plus. So you also have to ensure that the reactant is present, is your reactant or not. Similarly, now I have to look at the lowest potential. The lowest potential is the one that's going to lose electrons. In this case, the lowest potential is coming out to be minus 1.20 volts. So this is the one that's going to lose electrons, and if it wants to lose electrons, it must go in the backward direction to lose electrons. And I need to ensure that the reactant in this electrode, vanadium, the one that is losing electrons, is also present as my reactant. So I'm going to select both equations. the higher potential equation, the one that is gaining electron, getting reduced, and the lower potential equation, the one that is losing electrons and getting oxidized. I'm going to select the two equations and make an overall equation. Moving to step 3. Step 3 is you need to balance the number of electrons that are gained and the number of electrons that are lost, and you have to write an overall equation. So if you look at the two reactions that I've selected, the higher potential one that is gaining electrons and the one that is getting oxidized or losing electrons, you would notice that Fe3 plus is only gaining just one electron, whereas V is losing 2 electrons. So I need to balance the number of electrons that are gained and lost. So for that, I would need to multiply this equation by 2. If I multiply the entire equation by 2, then the number of electrons that are being gained and the number of electrons that are being lost, they become equal. Once the electrons gained and lost become equal, what you just need to do is you need to write an overall equation. You just sum up the reactants and sum up the products, and that would be your overall equation. So in the first reaction, your reactants are the 2Fe3 plus 2 electrons. So those are your reactants. So I'm going to write that down. It's going to be 2Fe plus 3 plus 2 electrons. And in the other half reaction, the reactant is vanadium. Vanadium is the one that's losing electrons. So vanadium is your reactant. So I'm going to add that as well. So that is my reactant in the second half equation. And then I'm going to sum up the products. My products in the first reaction, they are 2Fe plus 2, that they are being formed. In the second half reaction, the products are V2 plus 2 electrons. So I'm going to sum the products up. It's going to be 2Fe plus 2 plus V2 plus is the product in the second half reaction plus 2 electrons. Now these electrons, because they're equal, they will get cancelled out. So if I remove that, so without those electrons, that would be my overall reaction. It's going to be 2Fe plus 3 plus vanadium, forming 2Fe plus 2 and V2 plus. So this is the overall reaction that's occurring when vanadium reacts with Fe plus 3. I will also try to calculate the overall E0 cell for this reaction. If I want to calculate the overall E0 cell, E0 cell is higher potential minus lower potential. So if you look at the two electrode, half electrode reactions, the higher potential is 0.77 volts, the lower potential is minus 1.20 volts. So it's going to be the difference, higher potential minus lower potential, or 0.77 volts minus the lower potential, which in this case is minus 1.20 volts. And the answer that I'm going to get is 1.92 volts. So my answer comes out to be 1.92 volts. And this is a very high E0 cell, which means that this reaction is very feasible. The higher the E0 cell, the faster or more feasible the reaction is going to be. So this reaction, which we have written over here, is going to be a very feasible reaction where Fe plus 3 gets reduced to Fe plus 2 and vanadium gets oxidized to vanadium 2 plus. Now I'm going to quickly summarize the overall reaction that has so far happened. We were reacting Fe3 plus with vanadium, and the overall equation that we got was that Fe3 plus aqueous was getting reduced to Fe2 plus. It was gaining electrons, and vanadium was the one that was getting oxidized and forming V2 plus. And the E0 cell of this entire reaction came out to be 1.97 volts, which meant that this reaction was very feasible. Now in step 2 of this same reaction, what I'm going to try and do is that my products are, in the first step, my products were vanadium 2 plus. So vanadium 2 plus is one of my products in aqueous state. The other product is Fe2 plus. So that is also my product in the first step. And let's say some of the reactants which were Fe3 plus, because we were initially reacting Fe3 plus aqueous and it was in excess, which means that some of the Fe3 plus is also left over. So if you look or observe carefully, you would notice that these two are my reactants from the first step, products from the first step. Vanadium 2 plus and Fe2 plus are the products from the first step, and there's some leftover Fe3 plus present as well in the reaction. And I'm now going to try and do step 2. I'm going to try and figure out whether the products, would the products have another reaction. So I'm going to open the electrode potential table and try and figure out whether there is another reaction possible between the products that are formed and the leftover reactants from the first step. So this here is my starting point of step 2. These are the products that were formed from step 1, and this is the leftover Fe3 plus that was used as a reactant, but some of it was leftover. So we're going to try and figure out whether there's a reaction possible still. So let's open the data booklet and let's start marking or writing down the equations that electrode reactions that involve either V2 plus or Fe2 plus or Fe3 plus. I've opened the data booklet and let's search for V2 plus first. That's one of my reactants in step 2. So V2 plus, there are two equations two electrode reactions that involve V2 plus. So I'm going to copy those two reactions. Similarly, for Fe3 plus and Fe2 plus, these are the three electrodes that involve Fe3 plus and Fe2 plus. So I'm going to copy those electrodes with the electrode potential. So it's either Fe3 plus getting reduced or Fe2 plus getting oxidized, Fe3 plus. So I'm going to copy all the electrode reactions involving Fe3 plus and Fe2 plus. So I've copied all the reactions, electrode reactions that had Fe2 plus in them or Fe3 plus in them or V2 plus in them. So these are the list of all the electrode reactions containing these particular reactants. Now the rule is that the higher potential is the one that's going to gain electrons or get reduced. So I have these possibilities, these possible electrode reactions. The highest potential among them is shown by this electrode over here, which is 0.77 volts. So this is the one that's going to get reduced or gain electrons. So higher potential is the one that's going to gain electrons. So it's going to be Fe3 plus that would be gaining electrons. And I need to ensure that Fe3 plus is my reactant. So in my reactants, if you look at the reactants, Fe3 plus is present in the reactants. So out of these electrodes, it's Fe3 plus, that's the one that's going to gain electron because it is the highest potential. So this reaction would be in the forward direction and the reduction equation would be this one. So I've selected this reaction for gain of electrons or the substance that has the highest tendency to get reduced. Similarly, on the other end, lower potential is the one that's going to lose electrons. That would have the highest tendency to lose electrons or get oxidized. So if you look at all the electrode reactions, the lowest potential is shown by minus 1.20 volts. So this is your lowest potential. These are voltages, electrode potentials. So lowest potential, that's the one that's going to lose electron or have the highest tendency to lose electrons. But there is a problem. If I want to select this reaction for loss of electrons or for oxidation, it is the lowest potential, but there's a problem that I need vanadium as one of my reactants. Then vanadium would be the one that would be losing electrons. But if you look at the reactants that you have, there is no vanadium present. So I can't use this reaction because I don't have vanadium in my reactants. So make sure that the substance that's losing electrons is present in your reactants. It is not. If it is not, then just cut out that particular reaction. So moving on, again coming back to the same point, lower potential is the one that's going to lose electrons. So out of these, the lowest potential is now shown by minus 0.44 volts. So this is the reaction or electrode reaction that has the highest tendency to lose electrons. So it's going to go in the backward direction. It's going to try and lose electrons. And again, we encounter the same problem, although it is the lowest potential. But it's going to be Fe that would be losing electrons and a neutral Fe atom. But there is no Fe present. There is Fe2 plus present. There is Fe3 plus present, but there is no Fe present. So I cannot use this reaction because I don't have Fe as one of my reactants. So I'm going to remove that equation as well. Coming back to the same point, lower potential is the one that's going to lose electrons. The lowest potential is now shown by minus 0.26 volts. If you look at this reaction, it's going to lose electrons, so it's going to go in the backward direction. But now if you look at this reaction, it is the lowest potential. V2 plus is the one that's going to lose electrons. But do we have V2 plus in our reactants? We do have V2 plus in our reactants. So this reaction is matching our reactants which were given over here. V2 plus would be the one that would lose electrons, and we do have V2 plus as one of the reactants. So I'm going to select this equation for oxidation, and I'm going to select this electrode reaction for reduction. So I've removed the rest of the electrodes. Finally, I figured out which one is going to gain electrons and which one is going to lose electrons. I just need to write an overall equation now. The first thing is I need to balance the number of electrons lost. In this case, the number of electrons lost are 1, and the number of electrons gained in the second reaction, the number of electrons gained are also 1. So the number of electrons gained and lost are equal. I just need to write an overall equation now. To write the overall equation, I just need to sum up the reactants. So I collect all the reactants and I collect all the products, and that would be my overall equation. So in the first reaction, the reactant is V2 plus, and in the second reaction, the reactant is Fe3 plus. So it's going to be V2 plus Fe3 plus. So these are my reactants, and I'm going to sum up the products now. The products in the first reaction are V3 plus, that's being formed in the first reaction. In the second reaction, the product comes out to be Fe2 plus. So that would be my overall equation for this reaction. And we can also try and calculate an E0 cell for this particular reaction. E0 cell would be higher potential, which in this case is 0.77 volts, minus the lower potential, which in this case is minus 0.26. So higher minus lower is going to be 0.77 minus 0.26. And the answer that I'm going to get is 1.03 volts. So that's a relatively high electrode potential, which means that this reaction is also is very feasible. So this is the second step. In step 2, the products that were formed in the first step and the excess leftover reactants, they're again reacting, and another reaction is taking place, which is this one. The V2 plus formed in the first step is now further oxidized to V3 plus, and the Fe3 plus, that was my reactant which was in excess, is getting reduced to Fe2 plus. So the overall summary of the reactions so far is, in step 1 you had Fe3 plus and it was oxidizing V2 plus, and that V2 plus in step 2 is now further oxidized to Fe3 plus when it reacts with Fe3 plus again. So the product formed from the first step is now further oxidized to V3 plus. Now after step 2, after doing step 2, after this reaction, what's left in the solution is that you have V3 plus formed, you have Fe2 plus formed, and there might be still some of the leftover excess Fe3 plus remaining in the solution. So now I'm going to try and figure out whether there's going to be a step 3, whether there's going to be another reaction that would take place between these ions. Now my solution contains V3 plus aqueous ions, Fe2 plus aqueous ions, and Fe3 plus aqueous ions. So I'm going to now move to step 1. These are my reactants in the solution. I'm going to move to step 1. I'm going to try and figure out the reaction between these ions. So the first step is I'm going to write down all electrode reactions that involve V3 plus, Fe2 plus, and Fe3 plus. So referring to the data booklet again, I have marked the reactions that involve Fe3 plus ions or Fe2 plus ions. So these are the 3 electrode reactions that involve Fe2 plus or Fe3 plus. So I'm going to write down these electrode reactions, and then I'm going to try and figure out what are the electrode reactions involving V3 plus. And I have found the reactions that have V3 plus. So there's one reaction over here, electrode reaction, where V3 plus is changing into V2 plus. There's another electrode reaction over here where V3 plus is getting oxidized, it's losing electrons to form VO2 plus. So I'm going to write down these 2 electrode reactions. So here I've written down the reactions that involved V3 plus, Fe2 plus, and Fe3 plus. So all electrode reactions have been copied and written down, and the electrode potential values are also written down over here. And I'm now going to try and figure out which of the ions or substance or species gains electrons. So remember that higher potential is the one that has the highest tendency to gain electron or get reduced. Now if you look at all the equations over here, you would notice this first one is the highest potential, plus 0.77 volts. So the highest tendency for the substance out of all these that has the highest tendency to gain electron is going to be Fe3 plus, and that would be gaining electrons, and we need to ensure that Fe3 plus is part of our reactant, because Fe3 plus would be the one that would be gaining electrons to form Fe2 plus. So you can look over here that Fe3 plus is present in your solution, it is your reactant. So I'm going to select this equation for reduction. Fe3 plus would be the one that would be gaining electrons because it has the highest it has the highest electrode potential. So next I'm going to figure out which species is the one that's losing electrons. So it's the lowest electrode potential that loses electrons, has the highest tendency to lose electrons or get oxidized. So from all the substances whose electrodes are given over here, the lowest electrode potential is for this equation over here, minus 0.44 volt. So it's going to be Fe, that would be losing electrons. But now you also need to check if Fe is the one that's going to be losing electrons because it has the lowest potential. You need to check whether Fe is present in your reactants, and you would notice that your reactants, there is no Fe present, so this reaction does not match or fit your reaction that you have described. So I'm going to cut that equation out. I'm going to remove that particular reaction because it doesn't fit or it doesn't fit the reactants that are given to me. Now I've removed that. Again, going back, lowest potential is the one that's going to lose electrons, get oxidized. The lowest potential now is coming out is minus 0.26 volts. So it's for V2 plus. V2 plus would be the one that would be losing electrons in the backward direction. And again, we have a similar problem because if we select this electrode over here, it's going to be V2 plus that would be losing electrons, but your reactants, there are no V2 plus ions present. There is no V2 plus present, so I can't select this equation. I'm going to get rid of this equation because this does not fit or match my reactants. So let's remove that reaction as well. Again, going back, figuring out which one loses electrons. So lowest potential now out of the three leftover reactions is going to be minus 0.04. This is the lowest reaction. So it's going to be Fe that would be losing electrons. And again, we have a similar problem. We don't have Fe. There is no Fe present, so let's cut that equation out as well. Doesn't fit or match our reactants. Now the only possible equation left, the lowest potential one, is this one over here at 0.34 volts. So this must be the one that would be losing electrons. So it's going to go in the backward direction. It would be losing electrons, and my reactant now is V3 plus. It's V3 plus and water molecules. Now, are V3 plus ions present? If you look at your reactants, there is V3 plus ions present. So we're going to select this equation. I'm going to ignore water over here because all these ions are present in aqueous state. So water would be by default present in all the solution. So V3 plus combined with water would be the one that would be losing electrons. So we have V3 plus. And since all these ions are in aqueous solution, we also have water molecules. So this equation matches our reactants. It matches perfectly with our reactants. So highest potential is the one that's going to gain electrons. That was Fe3 plus. They had the highest tendency to gain electrons. Vice versa, you had V3 plus. That was the one that was losing electrons to form VO2 plus. So I'm going to pick these two reactions. I've selected the two half reactions, one for oxidation and one for reduction. The next step should be that I need to balance the number of electrons that are gained, which is 1 in this case. Fe3 plus is gaining just 1 electron, and I need to balance the number of electrons lost. V3 plus is losing 1 electron. So the number of electrons gained and the number of electrons lost, they are equal. So I don't need to do anything over there. They're already equal. I just now need to write the overall equation, which is basically that I need to sum up the reactants. So I need to add up all the reactants. I've already balanced the number of electrons gained. And on the other side, I need to sum up all the products of the equation, of the reaction, of the two half reactions. So let's look at the first reaction over here. Fe3 plus is your reactant. So that's my first reactant. It's Fe3 plus, aqueous state. In the other equation, the reactants are V3 plus and H2. Remember, this equation is going in the backward direction. So the reactants are V3 plus and water molecule. So those are my reactants, V3 plus 1 water molecule H2O. And now I'm going to sum up my products of the two half reactions. In the first reaction, the product is Fe2 plus. So Fe3 plus got reduced to Fe2 plus, let me correct that. And the product in the other half reaction, the products are VO2 plus and 2H plus. So it's VO2 with the positive charge plus 2H plus. I'm not going to write down the electrons lost and gained because they are equal. 1 electron gained, 1 electron lost, so they will eventually get cancelled out. So this is my overall reaction for step 3. Fe3 plus further reacted, got reduced to Fe2 plus, V3 plus further got oxidized, and they ended up forming VO2 plus. I can also now try and figure out the E0 cell for this particular reaction. The E0 cell is simply higher potential minus lower potential. So in this case, the E0 cell would come out to be equal to, the higher potential is 0.77 volts, the lower potential is 0.34. So it's going to be 0.77 minus 0.34 volts, and that would probably be equal to 0.43 volts. Again, although the E0 cell is not very high, but it is positive, so this reaction is also feasible, and this reaction would occur. It has a positive E0 cell. Now, trying to summarize all the steps that we have covered so far, this was step 3. We are on step 3 where Fe3 plus reacted with V3 plus to form these products. So I'm going to give you a brief summary of all the steps we have done so far. First, initially we had V3 plus reacting with V. Vanadium got oxidized to V2 plus. In the next step, V2 plus got oxidized to V3 plus, and then another reaction took place, and V3 plus then got further oxidized to V2 plus. So after the first 3 steps, the reactants that I have, or the products that I have in the solution, what do I have in solution? I have these ions. I have Fe2 plus, VO2 plus, and 2H plus ions in the solution. So in my solution, at the end of the third step, the products that are present are VO2 plus, H plus 1 ions, and Fe2 plus ions. And there must be some excess leftover Fe3 plus ions present as well. So now I'm going to try and do a step 4. I'm not sure whether there is a step 4, but I'm going to try and figure out whether there's going to be a step 4. These are the things that are present in the solution after step 3, and this is the excess leftover reactant Fe3 plus. So I'm going to try and figure out whether these substances would try and react with each other. I would also like to add a few corrections. This equation over here was incorrectly copied. This VO2 plus was actually 2 plus was the charge on the ion, so make sure you correct this. Similarly, this over here was actually 2 plus, and so my overall reaction was actually different. So, and similarly, I'm going to make this correction over here. This was VO2 with a positive charge on top. So please ensure that you have corrected this. So now after step 3, the products from step 3 are VO2 plus, H plus 1, and Fe2 plus, and there's excess reactant still leftovers, which is Fe3 plus. I'm going to try and figure out the reaction of the between the ions that are now present in the solution. And I've written down all the equations for Fe2 plus and Fe3 plus. I've written down all the electrode reactions. Similarly for VO2 plus, I've written down all electrode reactions involving VO with 2 plus positive charge, VO with 2 plus positive charge. So all the electrode reactions have been written down. Now I've made a few corrections in the electrode reactions. I had copied them incorrectly. Now coming back to the main point, which is that higher potential electrodes are the one that's going to gain electrons, lower potential is the one that's going to lose electron or get oxidized. So I'm going to try and figure out the highest potential electrode first. The last 2 electrodes are your highest potential electrodes. So they're the ones that are going to gain electrons. So both reactions, if they are trying to gain electrons, they'll go in the forward direction. Now the problem is that I don't have VO2 plus ion in my reactants, and I don't have VO3 minus in my reactant. So I will not be able to select these equations because there is VO with a plus 2 charge, but not VO2 with a plus 1 charge. So these 2 reactants are not present. They would not be able to gain electrons. So I'm not going to use these reactions. So I'm going to eliminate these reactions. They had the highest potential. They were supposed to gain electrons, but I don't have the reactants present with me. Now, based on the remaining 4 equations, which one is the highest potential? It's going to be 0.77. So this is the one that's going to gain electrons. So it's going to gain electrons and form Fe2 plus. So this is my highest potential. So I figured out who's gaining electrons. It's Fe3 plus that's gaining electrons, and I do have Fe3 plus as one of my reactants. Now I'm going to try and figure out the lower potential, the one that's going to lose electrons. Now based on these 4, since I've eliminated this one because it had the highest potential, it would always be gaining electrons. So I'm now going to try and figure out the lowest potential. Between these three, the lowest potential is minus 0.44. So Fe is the one that's going to lose electrons, but we don't have Fe. In my reactant, everywhere there is no Fe present. So I'm going to remove this equation, ignore this equation. This does not match my reaction. The next lowest potential is minus 0.04 volts. Again, if it was supposed to lose electrons, then it would be Fe that would be losing electrons, but we don't have any Fe. So let's get rid of this reaction as well. Now I'm left with two equations. The lowest potential is 0.34 volts. So V3 plus would be the one that would be losing electrons. And if it were to lose electrons, it would form VO2 plus. But again, the problem is we don't have any V3 plus in my reactants. So I will not be able to select this equation. This equation will not fit the description of my reactants. So basically I have no equation left. There's no one ready to lose electrons. So this reaction pretty much ends over here. There's not going to be any step 4. So there were just 3 steps for this particular reaction, because when you try to figure out the 4th step, none of the reactants were actually reacting with each other. There was one that we figured out was going to gain electrons, but there was no equation where we could figure out which substance would be losing electrons. So the reaction ends over here. There is no step 4. So my reaction only had step 1, step 2 and step 3. And even these 3 steps, this made this question very lengthy. And this was a very weird question given by CAIE. And this was just a 3-mark question. So you can figure out that this was a very stupid question where you had to do a lot of working to just to figure out which steps were involved. And even then this reaction is not finished yet. We still have to figure out the overall reaction, which is that I'm going to sum up step 1, step 2 and step 3. I'm going to add up all the reactants and I'm going to add up all the products. If I start doing that, you can figure out that's 2 Fe3 plus 1 Fe3 plus over here plus 1 Fe3 plus over here. So that's a total of, that will give you a total of 4 Fe3 plus ions. Then I have vanadium, then vanadium 2 plus. Then there's a vanadium 3 plus, and then I have H2O as my reactant. So these are all my reactants, and in my products I have 2 Fe2 plus, another Fe2 plus and another Fe2 plus. So that's a total of 4 Fe2 plus ions, and the other products are, there's V2 plus, there is V3 plus there is VO2 plus, and then there are hydrogen ions as well, 2H plus. And if you look at the equation, what's going to get cancelled out is V2 plus would get cancelled out, V3 plus would also get cancelled out. And if I rewrite the entire reaction, the overall reaction would be 4 Fe3 plus reacting with vanadium, which is V, reacting with H2O, and the products are 4 Fe2 plus, VO2 plus and 2H plus 1. So this is my overall equation for the reaction. I've summed up step 1, step 2 and step 3. I have summed up the reactants and I have added up all the products and written this overall equation for the reaction.